Hello everyone, thank you for attending my presentation. I have been presenting at ARMA since 2018 and it has always been a pleasure, mainly because the ARMA crowd is a focus group. There are big overlaps between the members' backgrounds, and this makes it easy to either present something to them or follow a presentation. I will begin my talk on my paper, Analysis of Transparent Gelatin as a Reservoir Analog for Hydraulic Fracturing Experiments, by a brief summary on the background of this project. In the mid-2010s, I was at the University of Texas doing my master's in petroleum engineering, and I ended up performing a series of experiments on gelatin blocks of high concentration, about between 7 and 8% by weight. This created a transparent, brittle, and cheap polymer. As you see here, I had a aluminum tube going through the sample, simulating a horizontal wellbore. The tube had perforations in it, had holes, and I was basically trying to make 3 fractures from each test. Before finalizing my decision to use gelatin blocks as the reservoir analog, I looked into different potential transparent reservoir analog materials such as urethane plastic, not to be confused with urethane rubber. This was proven to be too ductile for what I needed it to be. When you apply stress on this material, it deforms rather than breaks, and this is not how rocks behave. Another material was PMMA, which is basically bulletproof glass, and this was brittle, unlike urethane, but has very high tensile strength of about 10,000 psi. And this makes it very hard to break in with the equipment and apparatus that you find in a typical geomechanics lab. This was the laboratory setup I used. I had the fracturing fluid, which is dyed glycerin, in the accumulator and was driven into the perforated aluminum wellbore using a teledyne ISCO pump, using water, basically. I ended up finishing my master's in 2016. I wrote a thesis on those experiments. I never got the chance to convert that to a journal paper. I immediately proceeded to my PhD, and I ended up being transferred at LSU in 2018. I got my PhD in 2020, which was on a semi-analytical, semi-numerical topic, and I had never published the journal related to my master's degree. Therefore, after getting my PhD, the first task I gave myself was to convert my master's thesis to a journal paper, and I ended up publishing that at the JNGSE, or the Journal of Natural Gas Science and Engineering, in 2021, last summer. That opened the door for a couple of spin-off projects related to my master's work, and one of those is to look closely into the scalability of gelatin as a reservoir analog in terms of this kind of hydraulic fracturing experiments, and this is what this paper is about. Now, gelatin used as a reservoir analog in hydraulic fracturing experiments is nothing new. I have here 8 studies where experiments are presented where gelatin was used as a reservoir analog. I highlight 2 of those papers. The first one is Hubbert Willis, 1957, very famous paper, a paper that everybody knows about, everybody claims to have read, but not really everybody has read. And another one is Wu et al. From ARMA Symposium from 2008, which presented a series of experiments on layered blocks, very nice experiments. Now, every one of those papers presents experiments on gelatin blocks of different gelatin concentration, but none of those papers has a complete scaling analysis on how well those blocks at those concentrations match scale with typical real-world hydraulic fracture treatments. Now, Kavanagh in 2013 did perform a comprehensive scaling analysis on using gelatin as an analog for, as a rock analog for magmatic fracture intrusions, or dikes with an I. Those dikes are basically tensile fractures with magma as the fracturing fluid. And besides the complete scaling analysis, she presented a couple of correlations that can be used to evaluate the mechanical and fracture properties for gelatin at various concentrations. So I used her correlations to evaluate the mechanical and fracture properties for my gelatin blocks from the conditions I used during my master's degree. And I find the Young modulus to be 5.39 psi, critical stress intensity factor for mode 1 cracks to be 0.25 psi square root inch, and the Poisson ratio is constant regardless of gelatin concentration and approaches 0.5, which is the upper limit for a very elastic material, that is gelatin. Now, these are some snapshots from the 21 experiments I ran during my master's degree. You can see that the transparency is quite inhibited when you use highly concentrated samples. But I was able to read the fracture height and fracture length from each test and use that as an input to come up with a width function, and I use that to build visualization plots for the produced fracture geometries, and I did that in MATLAB. Now, moving into the dimensional scaling evaluations, which is the main topic of this paper, the primary topic of this paper, I borrowed the Patter's analysis from 1994, where he took the governing equations for planar simple hydraulic fracture propagation and derived a set of dimensionless groups that could be used for scaling analysis. These dimensionless groups can be evaluated for lab scale conditions and the corresponding field scale conditions, and then we can see how well those two numbers are close to each other. The closer these numbers are to each other, the more closer to 1 the lab to field ratio of those numbers would be, and that will indicate how good the scaling is. Basically, a lab to field ratio of 1 will indicate ideal scaling for that particular dimensionless group. We use 4 dimensionless groups from the pattern. The first one is the treatment time, N sub D equals to injection flow rate Q times the injection time duration delta T divided by wellbore radius RW to the power of 3. Then we have the crack formation energy N sub gamma, which is equal to the critical stress intensity factor for mode 1 cracks K1C square divided by 4G square RW. G is a modified version of the bulk modulus that the pattern shorthanded to make the derivations easier to follow and cleaner. it still has dimensions of PSI, of pressure dimensions, and he called it the fracture propagation modulus. The third dimensionless group is the elastic deformation, Sn sub g equals to g Rw to the power of 3 divided by Q times the viscosity, the effective viscosity of the fracturing fluid mu bar, and that is for a flow into a planar fracture. And finally, the confining stress dimensionless group N sigma sub C, which is equal to the confining stress sigma sub C divided by the fracture modulus G. Now I took the parameters from my master's experiments and I compared them against typical field operation parameters from a slickwater fracture treatment and a crosslink gel fracture treatment from the Barnett shale, and we found that the crosslink gel treatment scales better against my master's experiments compared to the slickwater fracture treatment. And we see that here the magnitude orders apart for each dimensionless group for the slickwater and the crosslink gel. When we see the elastic deformation dimensionless group goes from being 6 orders of magnitude apart for the slickwater fracture treatment to only 4 orders of magnitude apart for the crosslink gel fracture treatment. The other dimensionless groups are 2 orders of magnitude apart for the treatment time, 1 order of magnitude apart for the confining stress, and 5 orders of magnitude apart for the crack formation energy. Those results are by no means ideal. We see that the fracture toughness imposes a higher impact under laboratory conditions than field operations, and viscous effects they impose lower impact under laboratory conditions and high compared to field operations. This implies that if we use a higher fracturing fluid viscosity at the laboratory, we are able to reduce the impact of fracture toughness and compensate for the lower laboratory injection flow rates. Then I use Excel's solver built-in function to come up with a set of laboratory conditions that will optimize scaling. For those of you who are not familiar with Excel's built-in solver function, this allows you to vary a set of parameters within a certain of predefined constraints to achieve a target value. So basically, when I say predefined constraints, you can constrain the variation of several parameters to stay within the logical range of typical laboratory apparatus and equipment and get the results to reach a certain target. In this case, the targets will be such that the lab to field ratios of the dimensionless groups come as close as possible to 1. I used a higher gelatin concentration of 18 to 19% by weight in my estimations. This will yield a higher Young modulus and critical stress intensity factor, as we see from the correlations of Kavanagh, but there would be added transparency and mixing challenges. I don't believe those would be detrimental, but they will be very hard to, they'll be quite hard to overcome. And as a result, I was able to get all dimensionless groups within the same order of magnitude when compared to the crosslinked gel fracture treatment, except the dimensionless group for the crack formation energy, which was decreased, but still remains 4 orders of magnitude apart between the difference between laboratory scale to field scale. In conclusion, the scalability of gelatin for the conditions used in my master's work is more favorable against typical cross-linked gel fracture treatment, which has higher fracturing fluid viscosity and despite a lower injection flow rate compared to a typical slickwater field operation. The lab scale experiments are predisposed towards overemphasizing fracture toughness over viscous effects. Using a high fracturing fluid viscosity in the laboratory improves scaling, and a set of lab scale conditions is proposed for optimizing experiment scalability compared to the field operations at a higher gelatin concentration of 18 to 19% by weight. And with that, thank you very much, and I hope to see you all next year in person, and I hope to have more than one presentation. Thank you.